This research introduces a novel class of electromechanical metamaterials, enabling direct control of total stress reduction through the application of an electric field counteracting mechanical stress. The material combines insulating and conducting materials, allowing for the manipulation of mechanical stress within the bulk material by applying an electric field generated by the conducting material. A unit cell consists of an insulating material cube surrounded by a conducting capacitor in each spatial direction, enabling arbitrary control of the electric field direction. The mechanical stress within the bulk material is assumed constant, enabling stress reduction. The paper formulates a minimization problem to determine the electric field that minimizes the total stress, which is written as the sum of the mechanical stress tensor and the Maxwell stress tensor, resulting in a symmetric tensor. The minimization problem involves finding the electric field that minimizes the Frobenius norm of the total stress tensor. The necessary condition for the minimization is derived, and the problem is solved by writing the Maxwell stress tensor in index notation using the Einstein summation convention. The derivative of the Maxwell stress tensor with respect to the electric field is calculated, and the resulting equation is simplified to obtain an eigenvalue problem for the mechanical stress tensor. The authors investigate the minimization problem with additional constraints, allowing only tensile or compressive stresses, respectively, and consider the two-dimensional case of plane stress. They discuss their findings and the extent to which the mechanical stress can be reduced. The paper then focuses on the minimization of electromechanical stress in a dielectric material subjected to an external electric field. The problem is approached by using the Maxwell stress tensor, and the goal is to find the optimal electric field that minimizes the total stress in the material. The authors consider the cases of nonpolarizable materials, tensile stress, and compressive stress, deriving the optimal electric field solutions using the Karish-Kuhn-Tucker conditions and Lagrangian formulation. The results provide a comprehensive analysis of the electromechanical stress minimization problem in dielectric materials. The research paper presents a comprehensive study on stress minimization in materials under various conditions, formulating the Lagrangian to minimize the stress tensor in 3 cases of compression. The first 2 cases involve different inequalities, while the third assumes positive eigenvalues. The authors then move on to the plane stress problem, where the material is under plane stress and the total stress is 0 in all z directions, formulating the Maxwell stress tensor and solving the optimization problem to obtain the optimal eigenvalue. Numerical results for the plane stress case show that the remaining stress is independent of the distance from the origin but depends on the angle with respect to the polar axis. The authors introduce polar coordinates to calculate the remaining stress and obtain an analytical solution. The average remaining stress is computed and compared to the 3-dimensional cases. In the 3-dimensional problems, the authors use spherical coordinates to calculate the relative stress, visualizing areas where nearly complete stress reduction is possible and areas where no solution can be found. The problem is solved numerically by randomly creating a sample of uniformly distributed points on the unit sphere. The paper presents a comprehensive analysis of stress reduction in 3-dimensional cases using a novel approach, showcasing 3 areas with very low remaining stress. The results are presented for unconstrained minimization, minimization of tension, and minimization of compression, with average remaining stresses of 0.70, 0.66, and 0.87, respectively. The discussion highlights the limitations of the approach, including the assumption of constant mechanical stress within the unit cell and the potential interference of the electric field from neighboring unit cells. The paper concludes by suggesting potential applications, such as robotic capsules for endoscopy or drug delivery in medical engineering, emphasizing the importance of sensor technology to automate the process. In the realm of transformation optics, researchers have successfully demonstrated the creation of cloaked electromagnetic, acoustic, and quantum amplifiers. This achievement showcases the potential for manipulating physical phenomena through innovative materials science. A seminal study by C.D. Johnston in 1968 provided insights into testing concrete in tension and compression, laying the foundation for understanding the mechanical properties of this ubiquitous construction material. Dorfman and Ogden's comprehensive treatise on the nonlinear theory of electroelastic and magnetoelastic interactions, published in 2014, offers a deep dive into the complex interplay between electromagnetic fields and mechanical stress in various materials. This seminal work has been instrumental in advancing our understanding of these interactions and their implications for material behavior. The concept of the Maxwell stress tensor for magnetoelastic materials was explored by Ho Man and Chudzika Adamczak in 2009, which is crucial for describing the distribution of electromagnetic forces within such materials, shedding light on their unique properties. A recent contribution to the field comes from Blaszczyk and Hackl, who introduced a novel class of electromechanical metamaterials designed to reduce stress through electric fields. This research opens up new avenues for the development of smart materials capable of self-regulation and adaptation. The generation of random stress tensors, as discussed by Gao and Harrison in 2017, plays a pivotal role in simulating realistic conditions for material testing. This methodology enables researchers to model complex scenarios more accurately, leading to a better understanding of material behavior under various loads. Moreover, the problem of generating uniform random points on the surface of a sphere, addressed by Tashiro in 1977, has far-reaching implications for computational geometry and statistical analysis. Lastly, advancements in robotics and drug delivery systems, as outlined by Cortegoso v. et al. In 2021, highlight the potential for innovative technologies to revolutionize healthcare. The development of robotic capsules designed for gastrointestinal drug delivery underscores the interdisciplinary nature of research, where insights from materials science, electromagnetism, and robotics converge to address pressing medical needs.